All right, so we've talked about Boyle's law already, and now we can kind of come back and rehash how this relates to kinetic molecular theory. I know I mentioned it on Monday, and I told you what that looks like, but really there's like a time lag for learning things. And so it's like I can lecture on something and I could tell you about something, or you could read something, and it usually takes like a day to sink in. And then you can kind of like reapproach it, and we can, coming between Monday and today, sort of come back to some of these topics, and hopefully they sink in a little deeper. All right, so we talked about kinetic molecular theory, and we have Boyle's law, which is the relationship between pressure and volume. So volume is proportional to 1 over pressure. And the reason for this is because a gas is a collection of particles in motion, and the pressure of that gas is actually the number of collisions against the walls of the container per some unit of time, per second, per minute, per hour. So this simulation, wrong buttons. This simulation has this thing, we can count the wall collisions. So up at the top left there. So we can see for this box right now, we're getting about 83 wall collisions per picosecond, or 10 picoseconds. Everything's to scale, so right, it's not actually 10 picoseconds, probably 10 seconds. And the pressure in this container is 5.1 atmospheres. You can see that at the top right. So if I do anything that increases the number of collisions, that will increase the pressure. So I can take this box and I can shrink it. So make the box smaller. Now our pressure goes up to 10 atmospheres. And if we count the number of collisions in that same 10 seconds, it's now 117 collisions. So if I increase the temperature, how is that going to affect the number of collisions and the pressure? Speeds up the gas. Yeah, so the particles are moving faster, which means that they'll have more energy. So every collision that one of these faster particles has with the wall will strike it with more energy. And they're moving faster, so they're bouncing from one side of the container to the other more often. So let's heat this up. So it's at 261 Kelvin. And let's just heat it up to 663. And you can kind of see that the particles are moving faster. The pressure's gone up to 25 atmospheres, where we were at 10. And the number of collisions has also gone up to 198. So pressure is a result of all of these particles smacking into the sides. What I think is really interesting and great about the simulation is every once in a while you get a particle that's moving really slow. So they'll like move really, really slow until they get hit by something, and then they take off. So not all of the particles in a gas are moving at the same speed. So when we talk about temperature, it's actually essentially the average of the speeds, or the kinetic energy of the particles. All right, the other one we talked about, so that's volume and pressure. We also talked about Charles' law. I guess I'm going to just write these in between. So we also talked about Charles' law, which is the relationship. So volume is proportional to temperature. Now for some of these things, if I go back to the simulation, do we have fixed? I think right now temperature is fixed. Yeah. So when we were making these changes, we didn't change the number of particles in the box. So we have 50 particles in the box, and we had the temperature is constant. For Charles' law, it's a little bit different. Instead of having temperature and the number of particles constant, it's the pressure. I think I want this one, yeah. It's pressure that remains constant. So if I increase the size of this box, the temperature has to increase to keep the pressure the same. Or if I decrease the size of the box, the temperature has to drop to keep the pressure the same. And actually, let's cool this back down. So for Charles' law, volume is proportional to temperature. So if I increase the volume, I have to increase the temperature to keep pressure and temperature, or pressure and volume constant. Or sorry, pressure and the number of moles constant. So if I set this back to constant temperature, constant. Oh, I see. Because we have to do one or the other. So if I set this to constant pressure, and then we want the volume to change accordingly. So if I increase the temperature, what's going to happen to the size of the box? It's going to get larger. Increasing temperature, larger box. And when we do this, because pressure is staying constant, how is the number of wall collisions going to be affected? So if we're at 126 right now and I cool this back down, is it going to be more, fewer, or the same number of wall collisions? If I decrease the temperature and therefore decrease the volume, it should be roughly the same. It's going to be a little bit different because the speed of the particles also plays a role. This is kind of like a balloon, and we actually had one of these, had this in a slide. I said slide so weird. Go back all the way down to Charles' law now. So Charles' law, volume and temperature. So that simulation is essentially a model of what happens inside of a balloon. So for a balloon, the pressure inside the balloon always matches the pressure outside the balloon. So if you cool down the balloon and the particles are moving slower, then the volume of the balloon shrinks to keep the pressure the same as the pressure outside. If you heat the balloon up, then the balloon expands, and so the volume's changing, but pressure stays the same, and then as long as there's not a hole in the balloon, the number of moles of gas, the number of particles stays the same. And that's because the particles inside the balloon can't collide with the inside of the balloon as hard as the particles outside the balloon are colliding with it. So they're always balancing that. All right, we'll go back to that a few more times. So, as I highlighted with all of these gas laws, the important thing is to recognize what units you have and which of the gas laws that matches. So if we have a gas cylinder with a movable piston, has an initial volume of 88.2 milliliters and is heated from 36 degrees Celsius to 155 degrees Celsius, what is the final volume of the gas in milliliters? So what units do we have? Here we have volume, 88.2 milliliters. And then we want to find a final volume in milliliters. All right, so those are volumes. Yeah, V1 is going to be 88.2. And then we have temperatures. So it's heated from 36 degrees C to 155 degrees C. So our T1 is going to be the 36 degrees C. V2 is going to be what we're looking for in milliliters. T2 is going to be 155 degrees C. Are those units going to work for Charles' law? Or do we need to convert some units? Yeah, Celsius has to be converted to Kelvin. The problem with Celsius is it's a relative scale. And so 0 degrees Celsius was chosen somewhat arbitrarily as the freezing point of water. Kelvin, though, is a relationship between the motion of the particles and the temperature. So there's an absolute 0 for Kelvin. So there's no such thing as negative Kelvin. And that's important for this Charles law. So we can take this and say 36 degrees C plus 273.15. So our temperature (36 plus 273.15) is going to be 309.15. And then 155 plus 273 is going to be 428.15. So these are Kelvin. And then just need to remember what Charles' law is, or what's the relationship between temperature and volume. It's going to be T1 V1 equals T2 V2. Sort of the formally stated law, but we can also flip both sides so that it's volume over temperature. And as long as we flip both sides, it ends up being the same thing. So then why would you want to flip it? If you flip it, then it's a little bit easier to solve because we want to find volume for this problem. So if volume is on top, then it's just a little bit simpler to do the algebra. So V1 over T1 equals V2 over T2 is the same thing.
So how would it make it easier to solve if it's on the top and the bottom? Like, I don't understand why that matters.
Yeah, so let's do both. And I'll show you. So for our T1, that's going to be 309.15 Kelvin over 88.2 milliliters. And then this is going to be 428.15 over V2. That's also Kelvin. And then this other one will be just that flipped on its head. So it's going to be 88.2 milliliters over 309.15 Kelvin equals V2 over 428.15 Kelvin. So if we solve this left one first, V2 is in the denominator here, so we have to get it into the numerator. So we need to multiply both sides by V2 to move it over here. So if we multiply by V2, multiply by V2, these will cancel and we'll get V2 times 309.15 Kelvin over 88. And you could have simplified the 88.2 milliliters in Kelvin before this, but 428.15 Kelvin. And then again, I'm going to keep the units in here. So I'm going to do 309.15 309.15 divided by 88.2. So V2 times, yeah, I can do that. 3.505, and this is now Kelvin per milliliter equals 428.15 Kelvin. So then need to divide both sides by the 3.505 Kelvin per milliliter. So then 428.15 divided by 3.505. V2 is 122. How many significants? Yeah, 3 milliliters. On this other one, we can start by simplifying these, which we could have done on the other one. That's not what makes this one different, but 88.2 divided by 309.15. Yeah. Will be, well, 0.2853. Now it's milliliter over Kelvin. I'm going through these very stepwise to show you that the units cancel out, which is the magic of gas laws. So then we multiply both sides by 428 Kelvin. All right, so this Kelvin cancel out with that Kelvin to leave us with just milliliters. This is going to be 122 milliliters equals V2. So if you don't flip it, then you have essentially 1, 2, 3 steps. If you do flip it, then you have 2 steps. So it just cuts out 1 step of trying to get the V2 on top. Yeah?
Isn't it like infinitely easier just to cross multiply and divide? Then that way you don't have to worry about the butt order of since it's a proportion.
Oh,
Right, sort of. That way you don't have to do that extra step of having to do the same thing.
yes.
That's what I was thinking too, that's what I was like,
I see. Whatever, I guess the main point is there's a lot of liberty you can take with how you solve these problems. For some people, it's easier to just get the V2 on top and then solve from there. If that's not you, you don't have to do that. Either way you do it, and this is one of those things, it's good to just prove it to yourself. Try some things out, see how the units cancel. Prove to yourself that the units do actually just cancel and work out. So get 122 either way. Okay. Right, so now we've got Boyle's law, Charles' law, and now we can look at the combined gas law, which takes Charles' law and Boyle's law and puts them together, because let me do it here. If Boyle's law is the relationship between pressure and volume, and Charles' law is the relationship between temperature and volume, then it's pretty reasonable to believe that there's a relationship between temperature and pressure as well. And that all 3 of these variables, pressure, volume, and temperature, are related somehow. So this is the combined gas law. And now we can take an initial condition that has pressure, volume, and temperature, and we can change 2 variables and calculate what the third one is under the new conditions. So we could increase the temperature, we could increase the pressure, and we could see how that changes the volume. Or we could increase the pressure, decrease the temperature, see how that changes the volume. All right, we can plug in any 2 pairs of conditions and find the result. The other nice thing about the combined gas law, and we'll see this again later, is that it contains Charles' law and Boyle's law, right? I mean, it's made up of the 2. But the conditions for Charles' law were constant pressure, and it's a variable we'll see later, but N, which is the number of moles. So same amount of gas, constant pressure. So if pressure in the combined gas law, it doesn't change. So let's say it's, this number is the same as this number. Then we can just move pressure, divide both sides by pressure, and the pressure will disappear, and you're left with Charles' law. Or for Boyle's law, the conditions are a constant temperature and a constant amount of gas. So if temperature is constant, right, this T1 is the same for both of these, then this, when it's multiplied to the other side, will cancel out. And actually, if I do something like this, I just block those out, that's Boyle's law. So Boyle's law and Charles' law are in here together, and if you hold one variable constant, it gives you those gas laws. So you don't need to remember Boyle's law or Charles' law independently. You just need to know the combined gas law, and that Boyle's law has constant pressure or constant temperature, Charles' law has constant pressure. Okay. So let's use this. This, of course, is where things get. Right now we can use the combined gas law with 3 different variables. So if we have a sample of gas with an initial volume of 158 milliliters, and milliliters is a unit of what? Volume. That's the question, because the kind of thing gets mixed up a lot, right? Just noting what type of variable it is very helpful for solving problems, especially gas law problems. And then at a pressure of 735 millimeters of mercury, and millimeters of mercury is a unit of what? Not temperature. Pressure. You might be thinking of a mercury thermometer. Oh yeah, a pressure of. Sometimes there are hints. Pressure of 735 millimeters of mercury and a temperature of 34 degrees C. Celsius, I think, you can always recognize as being temperature. And then we're given some new conditions. So if the gas is compressed to a volume of 108 milliliters and heated to a temperature of 85 degrees Celsius, what did I use for Celsius? Orange? What is the final pressure in milliliters of mercury? Millimeter. Yeah, millimeters. Green. So we can write this down as V1, let's go in order, P1, T1, V2, P2, T2. So our V1 is going to be 158 milliliters. Pressure is going to be 735 millimeters of mercury. And we'll have a temperature, 1 of 34 degrees Celsius. And then we're compressing to 108 milliliters. Heating to a temperature of 85 degrees C. And then we want to find the millimeters of mercury. So pressure 2. mmHg, millimeters of mercury. So without even writing any numbers down, do you think the pressure is going to be higher or lower? Well, if the temperature starts at 34 degrees Celsius, increases to 85, and it's moving. Particles are moving faster, have more energy, so they hit the sides more often. They hit them harder. And then the volume, Right, so based on the temperature, we think it's going to increase, but we also changed the volume. So if the volume is going from 158 down to 108, is that going to increase the pressure or decrease the pressure? Why would it decrease the pressure? Why would it increase the pressure? It's getting smaller. So it's going from 158 down to 108. So think about the particles in the box.
It would increase the pressure because it's getting smaller, so the particles are moving faster.
They're moving faster, yeah. Well, and then they also, because the distance from one side to the other is shorter, so they can make more trips in between, more collisions.
It's like, okay, I think this is a good analogy.
All right.
If I stand in the kitchen and I chuck one of those bouncy balls, it's gonna take longer, but if I go in the bathroom, same force, chuck the bouncy ball, chances are I'm gonna get hit.
That's a great analogy.
Smaller space.
That's a great analogy. Because then
That makes sense in my opinion.
changing the temperature is like throwing the bouncy ball slower. So if you just lob it, it'll bounce around, but not as fast. If you chuck the bouncy ball, yeah.
In the bathroom.
In the bathroom especially. So we're going
Like it's a half bath.
We're going from the kitchen, half bath. We're going from the kitchen and we're just tossing it to the bathroom and chucking it. Right? So there's a lot more pressure to not get hit by the bouncy ball.
Especially if it's one of those big ones.
Well, if it's one of those, you're going to break something. Yeah, that is a great analogy.
You gotta take chances in chemistry.
Okay, so 158. So, or actually, let me write the equation down first.
The only thing that would change would be the temperature, right? If you change the temperature, then it'll slow it down, even though you're in the bathroom.
Yeah, okay, so like if you're in the kitchen, it's probably a little bit cooler because there's more space, but if you're in the bathroom, you're usually hotter, like if you're something, you know, so if you get hit by that ball, it's gonna hurt, and it's gonna be hot, leave a red mark.
Uh-huh.
I meant that.
This is a good analogy. I like it. I do like it a lot. Okay, so this is the combined gas law. We know we need to use the combined gas law because we're changing two things and looking for how that changes a third thing. Right, so we changed volume, we changed temperature. What's the effect on pressure? So our V1 we can plug in here. And then our P1 we can plug in.
The temperature you change it to Kelvin, right?
Yes. I was waiting for somebody to say something. Most of the time I'm joking about waiting to see if somebody actually checks that, but this time I actually was waiting. So, yeah, we do need to change the temperature to Kelvin. So 34 plus 273.15, and that's going to be 307.15. And then 85 plus 273.15. So that's going to be 358.15. So this is going to be 307.15 equals 108 milliliters. Pressure 2 is what we're looking for, and then 358.15 Kelvin. So if we multiply, again, multiple ways to do this, but we multiply Kelvin over on both sides. And actually, I'm just going to, so 358.15. So you don't actually have to multiply anything until the end. And then we're also going to need to divide both sides by 108. So this is going to be, is this more complicated?
Yeah. Could you just have a one, I don't know how you said there's multiple ways, but wouldn't the easier way would be to do the,
Yeah, you could
Divided by that bottom number?
multiply those two and then divide by the 307. So I did this to just leave these Kelvin, 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 milliliters, milliliters. The only remaining unit is millimeters of mercury, and that's the pressure that we want. So there's some relationships that you have to remember in terms of volume and pressure, volume and temperature, whether it's an inverse or proportional relationship. But you could realistically, if you knew that, do these without the equation, just by canceling the units.
Oh, because otherwise your answer would be millimeters and mercury and Kelvin, huh? All three?
If you left one out.
If I would have done.
No,
the same.
that'll work too. Because when you multiply two different types of units together, they don't cancel out. So then you would get, well, actually here, I can show you, that's what I did up here. So when I'm divided 309 by 88.2, I got this 3.505, but I kept Kelvin divided by milliliters.
But on the other one, how do you get, you would have to keep all three, right? Like you would have to keep the mercury.
Oh,
you would have to
yes.
keep the millimeters and.
I see what you're saying. Yeah.
Can you do that? Can you
Yeah.
have all those three next to a number?
Mm-hmm. So if we had multiplied these two together, we would have gotten millimeters or milliliters times millimeters of mercury. And then when we divide by this, then the units of that would be milliliters times millimeters of mercury divided by Kelvin. And so you would keep all of those until you bring the numbers over from the other side and cancel them out. So 358.15 times 158 times 735. Excuse you, syntax error. Oh. So divide by 108, divide by 37.15. And this is going to be 1,254. Oh, it should actually be in scientific notation. But millimeters of mercury equals P2.
You can have a scientific notation on this?
Mm-hmm.
Doesn't matter.
So like this should be 1.25 times 10 to the 3 because of sig figs, millimeters of mercury. Because we only have, 3 sig figs. So our pressure did indeed go up, and it went up from 735 all the way up to 1,200. So got pretty close to doubling. $9.12, okay. So combined gas law. So if we have a balloon, has a volume of 3.7 liters at a pressure of 1.1 atmospheres and a temperature of 30 degrees Celsius. So right off the bat, right, we've got liters, atmospheres. I should really put the favorite bar. Can you do that? Is that here? Oh, there it is. Liters, atmospheres, and I already used that color, degrees Celsius. So if we take the balloon, we submerge it in water to a depth where the pressure is 4.7 atmospheres, and the temperature is 15 degrees C. Or what did I use for temperatures? Orange. What will its volume be? And so now we want to find that volume. Assume changes in pressure caused by the skin of the balloon. Oh, yeah. So this is talking about, well, we can ignore it. If the balloon gets colder, then it changes how elastic the balloon is. But this is still going to be the combined gas law because we still have 3 different variables here. So we've got volume, pressure, temperature. So we'll take those and we'll say we have, let's do P1, V1, T1, P2, V2, T2. So our pressure 1 is 1.1. The volume, 0.7 liters. And then our temperature, and let's just do this right off the bat, 30 degrees C, but again, it needs to be in Kelvin. So it's 273.15 plus 30, so 303.15. The final pressure is 4.7 atmospheres. The volume is what we're looking for, and that'll be in liters. And then our temperature is 15 plus 273.15. So 288.15 Kelvin. And the book will probably just say 273, and that's just a difference in precision. So 273.15 is just more sig figs than 273. So no reason to give up those sig figs. Okay, so P1, V1 over T1 equals P2, V2 over T2. And let's do it the other way this time, where we combine all the numbers on one side, and then we'll move the other numbers over. So we'll get 1.1 atmospheres, 3.7 liters over 303.15 Kelvin. And I think on gas law problems, more than other problems, including the units in your calculations is important. Pressure 4.7. V2 is what we're looking for, over 288.15 Kelvin. So now you do 1.1 times 3.7 divided by 303.15. So this is going to be 1.34 times 10 to the negative 2 atmospheres, liters per Kelvin. On the other side, we can do that also. We take 4.7 divided by 288.15. This will be 1.63 times 10 to the negative 2 atmospheres per Kelvin. Divide both sides by the 1.63.
On the left side, is that atmosphere like per liter?
Atmospheres times liters.
Okay, so does the V2 cancel out the liter? Because that's the second volume.
Well, we want to leave the liter because we're looking for the volume. Yeah. So we just take 1.34 times 10 to the minus 2 divided by 1.63 times 10 to the minus 2. And it's going to be 0.823 liters. And yeah, yes. Whatever works. Let me show you one of my favorite math tricks, because fractions are confusing. So if we take just the units that we had there, so the atmosphere times liters over Kelvin divided by atmospheres over Kelvin, it's kind of hard to see which things cancel out. So the trick is this. This division is the same thing as multiplying by this thing, but flipped upside down. So we can take atmosphere, liter, Kelvin, times Kelvin over atmospheres. That's the same thing as dividing, but now we can see that the atmospheres cancel and the Kelvin cancels much easier. That works for any division. Okay. So there's one last piece to this puzzle that we have to put in before we get to the ideal gas law, which you may have heard somebody say pivnert. That's the mnemonic for the ideal gas law. But before that, there's one thing that we haven't related to gases yet, and that's the amount of gas that's in each of these like balloons or cylinders or scuba tanks or whatever that we're talking about. And that has an effect on the volume, temperature, and pressure also. So Avogadro's law, the same Avogadro's number, he asked the question, what if the amount of gas changes? So if you add more gas into the balloon or take gas out of the balloon, how will that affect the volume, temperature, or pressure? So specifically for Avogadro's law, he said, how does the volume of the gas change with the number of moles of gas? So the number of actual gas particles. And it's a very nice linear relationship. So if you increase the number of moles, you increase the volume of the gas. And it's not just increase and increase, but if you double the moles of the gas, then you double the volume. So twice as many particles, twice as much volume. And actually, let's do this one first. So the volume of a gas sample increases linearly with the moles in the sample, first formally stated by Amadeo Avogadro, which is just so long ago. I mean, somewhere between there. So it assumes, like our other gas laws have assumed, different constants, but this is constant temperature, constant pressure. So the volume of a gas and amount of gas in the moles are directly proportional. And so direct proportion means V1 over N1, just like V1 over T1, same as Charles' law, same type of relationship, equals V2 over N2. And if I go back over to the simulation here, so currently we haven't messed with anything. Let's see, we want volume. Let me make sure that this is going to work. Yeah. So we haven't messed with the number of particles in the box. So I can go down here, and there's a little bike pump. And if I do one full pump, I think this will give us 50. So proportionally related. So if I add 50 more particles to this box, and we have 50 already, if pressure is constant, the volume should double. And sure enough, it does, although we don't have a way to measure the size of the box. The number of the collisions should also be the same. Or actually, no, should also close to double. And then, just like with a balloon, I can open this, and as particles start leaving through the top, the box slowly shrinks. So I can make this larger. All right, for every particle that leaves, oh, it's too small. All right, so and then we can add more. We pump this up. Oh, it changed this. Oh, I see. So you can increase this again. Oh, now it's too big. So it gets too big pretty fast. Huh? Yeah. Yeah. I'm going to explode the simulation. Oops. Can you switch back? There we go. All right, so direct relationship. And this one I think is makes the most intuitive sense, although I think these are all fairly intuitive. But this is why when you blow up a balloon, it gets larger. So for every doubling in volume of that balloon, you've doubled the amount of gas that you put into the balloon.
Is that why they get hot? Like, 'cause I have like a
The balloons get hot?
Well, I pull them up in an air compressor. I don't know if that has anything.
Oh, the process of compressing air makes things hot. And so then if your air compressor at first, you've just got like the tank. And so after you've used up enough of that, the air compressor has to kick on to replace the air. And so that air that gets replaced inside the tank is going to be hot from the compressor.
Is that why they pop more often than when it's just cold?
Possibly. Possibly. Right? So blow into a balloon, you add molecules, it gets bigger. That one makes sense. So if we have a 4.8 liter sample of helium gas containing 0.22 moles of helium, how many additional moles of helium gas must be added to the sample to obtain a volume of 6.4 liters? So we've got 4.8 liter sample, 0.22 moles, 6.4 liters. So the question is, how many additional moles of helium gas have to be added? So we're going to have V1, N1. How do they do this? Is it V on top, N on top? Oh, it's V on top. Okay. V2, N2. So our initial is going to be 4.8 liters. N1 is going to be 0.22 moles. And then the final volume that we're looking for is 6.4 liters. And so we need to know how many extra moles of helium do we have to add. And this one is just like, it's just like Charles' law, so relationship between volume and temperature, where we could flip this depending on how you want to solve it. So V1 over N1 equals V2 over N2, and we'll put 4.8 liters over 0.22 moles equals 6.4 liters over N2. And then yes, we can cross multiply, so we can take the N2 and multiply it up to the left, and the 0.22 moles multiply it up to the right. So we'll get 4.8 liters times N2 equals 6.4 times 0.22. This is going to be 1.408. And that's now, because we did moles times liters, this is going to be liter moles. And then we take that 1.408 and divide it by 4.8. So, whoops. N2 equals 0.29, I guess just 29 moles. And then this is where this question is a little bit tricky. What did we miss? How many additional moles? So we started with 0.22 moles. This, like many things, when you're trying to find like a change in something, it's going to be final minus initial. Did that with temperature way back. So to get to what was the volume here? To get up to 6.4 liters, we need to have 0.29 moles in the balloon, but we didn't need to add an additional 0.29 moles. We only have to add the difference between 0.29 and the 0.22 that we started with. So 0.07 moles. Yeah. So Avogadro's law. A lot of these end up solving the same way. The units do always magically work out. We'll do one more, Avogadro's law. So a chemical reaction occurring in a cylinder equipped with a movable piston produces 0.58 moles of a gaseous product. If the cylinder contained 0.11 moles of gas before the reaction and had an initial volume of 2.1 liters, what was the volume after the reaction? This is like a typical combustion engine.
Because when you give us a problems, you're not gonna tell us Avogadro's law or Boyle's law, right? We have
Right.
to figure out what law.
Exactly. Yeah. Although I will show you an easier way. So, right, we talked about how with the combined gas law, that was Charles' law and Boyle's law, you take those put together, and if you actually just plug in the numbers that you are given into that, usually something will be constant if it's not mentioned. So, or if you're not given numbers for it. So it doesn't change, so it doesn't matter, so you can drop it out of the equation, and it gives you Charles' law or Boyle's law. And we'll be able to do that when we add in Avogadro's law too. So for this one, we are going to be using Avogadro's. So we're going to have a V1 and an N1, V2 and an N2. And what is V1? So here it's 2.1 liters. And then what is N1? Yeah, this is where the wording of the problem is a little bit tricky because it mentions the final number of moles first. So it's not always the first volume or the first number of moles or the first pressure. You do have to read within the context of the question. So 2.1, 0.11 moles is the initial. And then V2 is going to be what we're looking for. And now the 0.58 is our final volume, or final number of moles, sorry. So V1 over N1 equals V2 over N2. So this will be 2.1 liters over 0.11 moles equals V2 over 0.58 moles. So 2.1 liters divided by 0.11 times 0.58. This is going to be 11, no, just 11. 11 liters equals V2. Cool.
So you would just do 2.1 divided by 0.11 times 0.5.
Mm-hmm. And then you get the moles canceling out, you're left with just liters. Okay, so we took pressure, volume, and temperature before, and we could relate those three things together. And now we have this Avogadro's law, which relates the number of moles to the volume. So we can now add that into a more complete gas law now. And that is the ideal gas law. Now, previously, our gas laws, we had to have an initial pressure, temperature, volume, number of moles, and we could find it for a final pressure, temperature, volume, or number of moles. Right? So we had to have a change in conditions. We say if you go from here to there, I can tell you what it is at the end. Or if we ended here and we started here, I can tell you something about the beginning, but you have to be going from A to B or B to A. The ideal gas law doesn't need an initial or final condition. We can just plug numbers in and it'll tell you for any of those variables what you're going to have. So we could calculate the pressure or the volume or the number of the moles or the temperature if we have the other three things. The reason we can do this is because of R. So R is a constant, it's the ideal gas law constant. And it's 0.0821 liters atmospheres per mole Kelvin. And that particular combination of units is important. It's part of why I've been writing out all the units for everything so far. Because if I take R and I multiply it by moles and multiply it by Kelvin and then divide by liters, I get atmospheres. So let me let's see here. So R, so that's also, like if I take so liters is volume, pressure, ATM is pressure, over, N is moles, T is Kelvin, VP equals NT, VP over NT. So this always equals 0.0821 atmospheres, liters per mole Kelvin. Oh, that's what it is. Yeah. See, I always write it atmosphere liter per mole Kelvin. The order of atmospheres and liters doesn't actually matter. But, I mean, for the sake of showing this for now, liters, atmospheres, mole Kelvin. So if I plug in a pressure, number of moles, and a temperature, then those units will all cancel out and leave you with volume. And so this is a relationship for all pressures, temperatures, volumes, numbers of moles. And you can also use this to find the other simple gas laws. We're going to do an example of that. Oh yeah, this kind of does that. Perfect. So if I take this now, and I'm going to write it as PV over NT, and let's call these each P1 V1 over N1 T1 equals P2 V2 over N2 T2. So if I make, for example, so if we want to know about volume and pressure for something, we make N and T constants. N, well actually I could just erase them. Right? So N and T are constants, so they don't matter for the equation. That gives us Boyle's law. Right, so this is Boyle's law. P1 V1 equals P2 V2. So let's put those back in. So now, if we say we want to know something about the, let's say, volume and temperature, so number of moles and the pressure are constant. So if number of moles and the pressure is constant, number of moles and pressure are constant, that gives you Charles' law. So V1 over T1 equals V2 over T2. So the simpler gas laws are really just pieces of the ideal gas law. And you can do that for all of these. But the great power of the ideal gas law, which is where that, I should say, PIVNERT, PV equals nRT, as it's usually written out. I think it's usually written that way to save space, because you can write it out as a single line. So in a question like this, the key that this is an ideal gas law problem is that we're just given 1 unit of moles, 1 pressure, and 1 temperature. And then we're asked to find the volume. So in all of our previous questions, it would say, take a balloon underwater. How does that change it? So we started on the surface. We knew what the pressure and the temperature was. You go underwater and you find out new temperature, and you try and find the pressure. But here we only have 1 set. So that's where we're going to use P, V, N, and T. So you can plug in a pressure, that's 1.37 atmospheres. You plug in a volume. Nope, can't plug in a volume because that's our unknown. So it says calculate a volume. And now is where units are going to matter more than they have for these simple gas laws. Because the units of R are always going to be atmosphere liter per mole Kelvin. Then N is going to be 0.845 moles, and T is going to be 315 Kelvin. So the units that you plug into the ideal gas law have to match the ideal gas law constant, because otherwise they don't cancel. So PV equals nRT. So 1.37 atmospheres times volume equals 0.845 moles times 0.0821, and that's atmospheres, liters per mole Kelvin, times 315 Kelvin. So we'll go through this one step at a time again. So we can take all of these numbers on the right side and multiply those together. And then how's that going to change the units? Yep, so we're going to cancel out the moles and Kelvin. Moles, moles, Kelvin, Kelvin. So 0.845 times 0.0821 times 315. So this is going to be 21.85. And then the units remaining are atmosphere and liters. On this side, we still have V, and we still have 1.37 atmospheres. So divide both sides by 1.37.
Does it matter which number you divide it with? If you one that one without any, or no?
Like if we had taken like these numbers and put them over, like divided to that side, or?
Like if you would have done the 2185 instead of the 137 underneath. Doesn't matter which one you move over.
Well, we needed to move, because V is the variable. So we wanted to move the 137 to the other side to get it by itself. Yeah. So then here now our atmospheres will cancel out. So and you should always keep all of the numbers in your calculator. So divide by 1.37. So V equals 1.5. Oh, calculators. 3 sig figs. So this is going to be 16.0 liters. That's the only unit left. So we got a little ways to go still. But we will finish this in lab then. We'll also have to finish Chem. Yeah, so we'll finish this in lab, and then we'll finish chapter 10 in lab also. I won't go so slow